Ok, este es el siguiente tema. Ah, el tema es Kinematics of Rotational Motion. Mm, Es muy parecido a lo que decíamos como Kinematics of Linear Motion o la descripción del movimiento lineal o en una dimensión, dos dimensiones, pero en este caso es específicamente para rotational motion, es decir, objetos que se encuentran girando de alguna forma. Es muy importante este tema no tanto por sí mismo, sino porque es base para el siguiente tema. Entonces, sí, sí es importante este tema otra vez. Según yo es un poquito más rápido que el pasado, pero vamos a ver. When we're talking about linear motion, sorry, rotational motion, or if you remember when we talked about linear motion before, we were saying that linear motion is going to be defined, for example, by displacement, that is just the initial point versus the final point, how much distance is between that. We talked about velocity, like distance over time, acceleration, that is how the velocity varies when you are, or when time is passing, like how much does the velocity increases or decreases. Um, and when we're talking about rotational motion, it has really similar concepts. Like you're just gonna change, like instead of displacement, you're gonna call it angular displacement. In this case, instead of measuring it in meters, you're gonna talk about radians or angles. It depends on, oh, sorry, on degrees. It depends on how you are talking about it. The velocity, you're gonna have angular velocity, and acceleration is gonna be angular acceleration. But actually, they are pretty similar to one another. But actually, like they are the same concepts, but for linear and rotational motion. But it's almost the same. Some things that are actually different are gonna be these two. Like the first one, this, let me open. Okay. When we're talking about this, or this formula is only telling us that frequency and time are, sorry, and period, because this is period specifically, um, are equivalent to one another, are proportional to one another, because like as it says down here, frequency is gonna be how many spins or turns is something given over time, or in just one period of time. In this case can be seconds. So for example, when we're talking about frequency, we're gonna talk about revolutions over second, for example, because it is that way. And the period is like the opposite of frequency. Like it's um, how much time do you require to do a whole spin or a whole turn or a whole revolution. And it is measured only in seconds. Only seconds. So, or is this? It is expressed in seconds. So they are equivalent to one another. Like if you have frequency, for example, and you wanna know the period of that phenomena, you just need to like, frequency is gonna be equal to 1 over period. And the other way around, if you want to get time having the frequency, it's gonna be 1 over frequency. But they are almost the same one another. So that is just that you can change things easily if you need to. And this other formula in the right is gonna be how you can change or how you can use time or frequency, sorry, period of frequency to obtain the velocity, the linear velocity of something. Like we're gonna see some formulas about angular velocity, but at the same time, like you don't need to get angular velocity in order to get linear velocity because they are related to one another too. So basically what you have to do, it's gonna be just multiplying everything by 2 pi radius. So I don't know if you remember, but in topic 7, we saw that to transform frequency into angular velocity, okay, let me write it by hand because it uses Greek letters. Like the angular displacement is gonna be equal to um, just 2 pi times a frequency. That is the formula for angular displacement. Like how many revolutions are you doing, and you multiply it by 2 pi. And that's gonna give you like the radians. Why? Because a radian is 2 pi, or equivalence. Its equivalence is 2 pi. So that's basically it. But to make it or to transform that into regular velocity, like linear velocity, you have to multiply that by the radius. Why? Because that's basically what you do every time to transform into linear or between linear and angular, to be transforming things between them. You just have to use the radius of the wheel or of the circle or the thing that it's spinning. So for example, if you want to get angular acceleration or angular velocity, what else is after? Also angular displacement. Okay. What you have to do is like, if you have that linear, form of that, you just have to divide it. Like you're gonna divide the regular form, like normal acceleration, so divided by the radius. And then for angular velocity, you just have to divide regular velocity by the radius. And for the angular displacement, you just have to divide like regular displacement, it can be d, for example, by the radius. So it is really easy to do the transformation between one and another. And the other way around, like if you have the angular one and you want the other, you just have to multiply. Like regular acceleration or linear acceleration is gonna be equal to the angular acceleration times a radius. Or if you want to get the linear velocity, you just have to multiply the angular velocity times a radius. That is a transformation that you have to do. So it is really easy. That's why, for example, if we have this, that if we have the frequency, instead of having to first estimate the angular velocity and then transform it into the linear velocity, we just can like multiply everything by radius, and you're gonna get everything that you want. So it is really easy to do. Okay. I'm gonna go to the next one. Okay. These are some formulas to estimate angular velocity, like how fast or the change in the spinning of something, like if it increases its spinning or if it decreases its spinning. So for example, here's one thing, like if you have frequencies, mm, you can just like multiply the difference in the frequencies, like initial and final frequencies, by 2 pi and then divide that over time, and you're gonna get your angular frequency. But if you have angular velocities, it's almost the same, right? You just have to get the difference in the angular velocities and then divide that by time. Just as in linear ones, if you get a negative sign here in the subtraction, that means that is like the spinning is deaccelerating. And if you get a positive sign, you're gonna get that it's accelerating. Okay. We already talked about this formula. One note that is important, we mentioned that in topic 7, but the most common units for frequency are gonna be RPM, or revolutions per minute. But we are not gonna be able to use that information, like use revolution per minute in the problems, because you want revolutions per second. Like second is the base form of the unit. So that's what we want to use. So what do we have to do? Only like divide these revolutions um, by 60, because there are 60 seconds in a minute, and you are gonna get uh, like how many revolutions per second you have. And that's the unit that we want to use. Okay. Yes. Something else, something else. No, I think that's enough. And we can do that example that we have here. Is a really simple example. I think it's even like insulting how easy this is. But we have that a block is lifted from rest until the angular velocity of the drum is 16 radians per second after 4 seconds. Like the time between rest and 60 radians per second was only 4 seconds. And they're telling us or asking us about the average angular acceleration. Just by looking at the information, we can know that it is accelerating and not deaccelerating, because it was in 0 and then it transformed into 16 radians per second. So it is accelerating. So radians per second is angular velocity. So we can use a formula with angular velocity. This one, that is the simplest one of all. So we just have to subtract final minus initial velocities over time. If we do that, if we take that information, we have that like angular acceleration. I don't know how to put that sign, but I'm gonna write it because that sign is alpha and it is angular acceleration equals the difference between final velocity, final angular velocity, that is gonna be 16 radians per second. Um, and this is subtracted by the initial one that is gonna be 0 radians per second. And we divide that by 4 seconds. That is the time that we have. So if we do all the estimation, let me open my calculator. We're gonna get that. Like, you don't need a calculator release, you have 16 minus 0, it's gonna be 16 over 4. You're gonna get alpha is gonna be equal to 4. But because it is an angular acceleration, the units for that are gonna be radians over a square second. Okay. So this is gonna be our angular acceleration, basically. And it is really easy to do, really easy to use. Okay, I hope that's clear. It is really, really, really easy to do. But we obviously like this is really easy and we can have more complicated problems, but and we're gonna get to those in a minute. Why? Because we can involve all of these formulas that we learned before. And we have, for example, that like all of these linear formulas that we have already been using since like topic 6, topic 7, topic 12 even. So we know these formulas. You have them already on your notebooks. It's really easy. We have like these ones are with x as distance or distance as x, but you can use y, you can use s, you can use d. It depends, right? Um, so if you look at this, the rotational formulas are going to be exactly the same as the linear ones. You have displacement equals initial velocity plus final velocity over 2, and all of that multiplied by time. And this is exactly the same. Angular displacement equals initial angular velocity plus final angular velocity over 2, and all of that multiplied by time. So it is exactly the same. We have final velocity, initial velocity, acceleration time, and we have final angular velocity, initial angular velocity, angular acceleration and time. So all of these formulas are just the same as the other ones. The difference is just um, the variables that you're using, like the letters you are using to express the variables, but they are almost the same. This one maybe it's gonna be like the one that we're gonna use the most because you're gonna have like displacement, initial velocity, time, acceleration, time squared, and it's exactly the same for a rotational one. So this is gonna be used a lot. But like the truth is you can use anyone that you can. Like for the ones you have enough information to apply it or to solve it. Uh, and just like a quick note, um, when we're talking about spinning and we're talking about velocity specifically, because if you remember, velocity is a vector quantity, so it has to have um, direction, right? So just as we use signs when we were talking about like the axis, like if they were moving north or south, left, right, up, down, all of those things. When we're talking about rotational motion, it's the same. And this is the convention, right? If you have, or if the spinning is being done clockwise, the sign is gonna be negative. What is clockwise? Well, the direction of the clock, right? So in this sense, if the thing is moving in this direction, it is gonna be a negative sign. But if the movement is being done the other way around, like counterclockwise, you're gonna have a positive sign. Okay, that is just a note that you may need for some problems if they give you ones. Okay. So, but yes, it was just a quick reminder, a quick note. And for example, we have a little problem that is a bit more complicated than the other one. And you have this information, right? That a drum rotates clockwise initially at 100 revolutions per minute, and then accelerates constantly to the other side at 3 radians per square second during 2 seconds. What is the angular displacement? Okay. What is the information that we have? We have a frequency, and that is important. Revolutions per minute is going to be frequency, okay? Some people are going to tell you that it is velocity or angular velocity, but it is not. You still need to transform that information to get an angular velocity. It is really easy to do. So that is why many people say that it is an angular velocity, but it is not an angular velocity, it is frequency. Okay, so we're gonna have like an initial frequency, right? angular frequency of 100 revolutions per minute. We also know that there is, well, before we move forward, if it is being moved clockwise, it is gonna have a negative sign, right? And then it accelerates constantly to the other side, so it is gonna be positive, right? We're gonna have an angular acceleration that is alpha, sign here, of 3 radians per second squared. And we have a time of 2 seconds. And they are asking us about the angular displacement. That is theta. That is this sign. We also know, well, alpha is gonna be this other sign. Okay. Okay, 3 radians per square second, meter seconds. What is the angular displacement? So we can just check the formulas that we have or the information that we have. And which formulas can we use, right? So for example, we have that, if we go back a little bit to check the formulas just quick, that is information that we have. So do we have initial velocity? We can get it from frequency. Let me put the focus. Okay. But do we have final velocity? No, and we can't estimate it easily because we don't have something to do that. Maybe we could use this to get final angular velocity because we have initial, we have acceleration, we have time. So maybe we can get it, but maybe there's an easier way that doesn't involve using or estimating final velocity because they are not asking us about that. They only ask us about angular displacement. So if we go, for example, to the next one, we check or we see that angular displacement equals angular velocity, like initial angular velocity time times time, plus half acceleration times square. So we have all that information. And the only thing that we're missing is angular displacement. So we can apply this formula, right? Okay, so we go back to the other slide. That's it. And we can start applying that formula, right? And we say, for example, that angular displacement, let me change the folder. Angular displacement equals initial angular velocity. Oh, okay, we are missing still to change the initial frequency to angular velocity. How do we do that? We said that we only have to multiply, right? And say that like initial angular velocity is gonna be equal to the like 2 pi and the frequency, right? So basically we have to multiply 2 times pi times this amount, 100 revolutions per minute, but it is in revolutions per minute and we don't want revolutions per second. So first we need to divide it by 60, right? So if we do that and we divide 100 over 60, we're gonna get 1.3, I think. 100 over 60, no, 1.6. So this multiplication down here is gonna be like angular velocity. So angular velocity, it's gonna be 2 times pi, that is 3.1415926, right? But let's put it like this. And the frequency is gonna be 1.6 revolutions per second because we divided it, like we divided the 100 by 60 to get revolutions per second instead of revolutions per minute. And don't forget to include the negative sign. So that is gonna be, let me do it too. times 3.1 times uh, it's gonna be negative 10.49. And this is gonna be radians per second. Okay. So now that we have that information, we can substitute it in the formula, right? Say, for example, that the formula said initial angular velocity. So we're gonna talk about negative 10.49 radians per second multiplied by the time that is 2 seconds. And then we add up a half, that is the same as 0.5. Angular acceleration, that is 3 radians per second, times the squared time, that is 2 squared for second squared. Okay, so we're gonna have that the first part is gonna be well, negative 20.98 or 99 even, we can put it like that. Radians plus 4 times 3, it's 12 times a half, it's 6, right? Yes, yes, 6 radians. So the final or the angular displacement that we're gonna have is gonna be negative, yes, because it is bigger, negative 14.99 radians. Okay. So this is, let's see. Okay. So that is the angular displacement that we have a negative of 14.99 radians. Why is it still negative? Because it didn't get the chance of stopping completely, so it couldn't start like spinning the other way around. It had to like keep spinning, but being slowed down a little bit. So at the end, you have that it is still moved the other way around. If the time was bigger, then maybe it would have stopped and then started going back again. But in this case, it didn't. It only kept advancing until it stopped, until it, like the time, we stopped counting the time. So it didn't get the chance to stop completely and it started spinning around to the other side. So that is it. We have the angular displacement now, only applying those formulas. So it is really easy to do also. Uh, in the classroom, we did a lot more examples. Well, like 3 more or something like that. Um, and we can see them if we're back in the classroom if you want to, if you need to. But it is basically the same. We just have to do it. So I hope this helps with understanding the topic. If you have any questions or something, just ask me. Okay, so that would be everything. Stop here and stop.